We're now going to open the software for the Pavement ME design software and go through some of the flexible pavement rehabilitation design strategies, look at some of the input values, and also look at the different rehabilitation input levels specifically for the Pavement ME design software. So we're going to open the software now, and this part of the presentation is noted, or this part of Module 9 will be noted Part B, or is noted Part B. So this is the software, the design type. We're going to start with, first of all, the basically reviewing the first overlay rehabilitation, the magnitude of the multiple overlays rehabilitation. These are going to be the two that we're going to cover first. And within this is going to be AC over AC. We have AC over seal coat interlayer. We also then have, in terms of the rigid overlays, JPCP over AC, CRCP over AC, and then short jointed plain concrete pavements over asphalt concrete pavements. So I'm going to enlarge the screen so we can maybe see the numbers a little bit better. So this is kind of what we're going to go over. So we're going to, first of all, we'll start with first overlay rehabilitation, asphalt on asphalt, or asphalt overlay of an existing flexible pavement. Performance criteria is basically the same. There's basically no difference other than for a new flexible pavement design, other than we have two additional design criteria or performance criteria. And this has to do with the reflection of existing fatigue cracks that includes both reflection cracks as well as new fatigue cracks that will be predicted at the surface of the asphalt overlay. And then the other is a total of reflection of transverse cracks and or shrinkage cracks in the existing pavement plus new thermal or transverse cracks in the existing layer. And for these two categories or performance criteria, that is where the reliability is applied. The reliability is not applied to just the AC bottom-up fatigue cracks of the asphalt overlay or new thermal cracks or transverse cracks in the new asphalt overlay. So the reliability is set at 50%, and you as a designer and or user cannot change these values. What the reliability is applied to is what we see and can measure at the surface of the pavement. And we can't see and measure or know if the new fatigue cracks or if the fatigue cracks at the surface are new, or if the transverse cracks located at the surface are new. So it's a combination of reflective and transverse and reflection and new fatigue and transverse cracks where the reliability is applied. The traffic, the climate, structure, basically those are all the same since we own the structure. Since we have the initial overlay, the initial structure is the new asphalt overlay and then the existing asphalt layer, and the user can enter multiple asphalt layers and then any other layer located below the surface that exists in the flexible pavement itself. The design properties, the design property for the asphalt layer basically are the same as for a new flexible pavement design. We have the layer interface, initially full friction is used. We would only use, and again, full friction has an interface friction value of 1. If there's no bond and we have total slip between two layers, that would be designated as a zero. For example, if we have or we expect debonding between the overlay and the existing asphalt layer, we put in 0. If, however, we simulated two existing asphalt layers and one is stripping and they're not bonded to good together, or the tack coat has degraded and there is no more bond, then 0 could be entered for between those two asphalt layers, and that would be full slip or represented at full slip. So originally the defaults are all 1s indicating full friction or full bond between all layers. We've already discussed under Module 6 on flexible pavements the endurance limit and the user's multi-layer rutting calibration coefficients. Those are the same as for new flexible design, so we're not going to repeat those. The other design property is rehabilitation, the rehabilitation screen. And this is in rehab input level 2, and we're going to define these more in detail further in the presentation. But the rehab input level, this is where it's entered. We can have 3 different levels. If we have mill thicknesses, this is where that is entered. And then what the condition of the existing pavement. Fatigue cracking, bottom-up fatigue cracks, the length of transverse cracking, and the severity level going from low, medium, high, or user-defined. That's where these values are entered, and we're going to include these or discuss these, explain these in more detail further in the presentation. The other is the amount of rutting in all of the existing asphalt layer. So if we're placing an overlay over an existing flexible pavement, there is no rutting in the overlay, our surface or top asphalt layer, so there's nothing to be entered. But in the default asphalt concrete or in the asphalt layers that exist, we would take the rutting measured at the surface and distribute it throughout the lower layers, however number of asphalt layers we have in the pavement structure, our existing base layers, whatever they are, and then however many subgrade layers we have or that in our pavement structure or simulated in our pavement structure. We would distribute the percentage of total rutting in each of these layers. And we'll discuss these later in the presentation, but these were already discussed in the general overview of pavement rehabilitation, as well as in the original, the inputs under Module 4.4 for distributing the rutting in each of the layers included in the pavement structure. So very briefly on calibration first. The calibration factors for new bottom-up AC cracking, top-down AC cracking are all the same as for new flexible pavement design. What is different is the reflective fatigue cracking asphalt layer, and these were discussed in Module 6-2 on semi-rigid pavements, where we initially discussed reflection cracking. So we're going to, again, within this section, overview the reflection cracking model and transfer function, but where the calibration coefficient go are under the calibration folder and under reflective fatigue cracking, as well as reflective transverse cracking for the different C factors, as well as the different K values for the stress intensity factors. For transverse cracking and then fatigue cracking, the calibration coefficients C1 through C5, and then the K1, K2, K3 for the stress intensity factors. That's where those get entered. The only other difference is on IRI, and where we have the IRI of asphalt overlays of flexible pavements, C1, C2, C3, C4, and then IRI of an asphalt overlay of semi-rigid pavements that we discussed in Module 6-2 on semi-rigid pavements, or asphalt overlays of rigid pavements that we discussed in Module 8 under rigid pavement rehabilitation. And that's the C1, C2, C3, C4 coefficients in the IRI regression equation. So all those are the same, and we're going to mention them but not discuss them in detail. So I want to go back now to the general information where we have the first overlay of a flexible pavement, AC over AC. And these are the dates that are generally required for all of the first overlay, first rehabilitation that's required for flexible pavements. Existing pavement construction date, the original construction, the proposed overlay construction date, and then the traffic opening date for the asphalt overlay. That's all the same, which was also discussed for the rigid pavement rehabilitation under Module 8. The one difference to this has to do with going to the multiple overlays or multiple rehabilitation. And that's where we may have existing asphalt overlays already placed on the flexible pavement, and we're designing another one. Or we already have an asphalt overlay of a jointed plain concrete pavement or a continuously reinforced concrete pavement or a semi-rigid pavement, and we're going to place or design and place a new overlay, and or we've placed an asphalt over our jointed plain concrete pavement that's fractured, crack and seat or break and seat, and then we're designing an additional overlay for that pavement structure. So I'm just going to note the AC over AC over AC for the multiple overlays. And what you can see is we have our date for the original pavement construction, just like for the single overlay. And then we have, though, the overlay construction date for the overlay or one or two overlays that are already there. If we already have two overlays that were placed at different dates, you as a designer and user must decide which overlay date is going to be entered. In general, this would be the latest overlay date that has already been placed and already exists, because we're entering the distress data that's measured on the latest overlay that has been placed. And then the last two are the proposed overlay construction date. That's the overlay we're designing now. And then the traffic opening date. So all of those are basically entered for each of the different, the single or multiple overlays. Just a quick illustration. If we have the multiple overlay option that was selected, we have our original structure, then we have a layer category for the overlays that have already been placed. In other words, they exist, and then we have our proposed overlay. So basically this is the new overlay is a one asphalt layer. The existing asphalt overlay is the second asphalt layer. And then the original asphalt layer is the third. and there's a maximum of 4 layers that can be used. So we only have one additional asphalt layer that can be simulated as the original, another layer in the original asphalt layer or structure, or maybe an additional layer of having 2 lifts or 2 different layers for our asphalt overlay. It could also be applied to the existing overlay that's already there, but it's more likely that 4th asphalt layer to be in the original asphalt layer structure or in the proposed asphalt overlay for which we're designing the rehabilitation strategy. So with that, we're now going to go back to the construction of the single layers. And I want to briefly mention the concrete layers and show those before we go back to the presentation. So first, overlay rehabilitation. Now we have a jointed plain concrete of the asphalt or the existing flexible pavement. We have our 3 dates. So I'm going to go back to the flexible pavement or to the pavement structure. And you can see now that we have our jointed plain concrete as the overlay, and we have our existing flexible pavement. And that's the structure. We also can use the CRCP of the asphalt overlay going to the structure, and basically it's very similar, but now we have a CRCP overlay of the existing flexible pavement, whatever the flexible pavement is. The inputs for the new CRCP or the existing JPCP and the existing design factors are all the same for the concrete overlay versus a new or the new CRCP and or new JPCP design. Those are basically the same. The rehabilitation is also going to be similar for the asphalt overlay of a flexible pavement. We have our rehabilitation input level that we're going to go over, the mill thickness for the asphalt that's already there, and then we have a amount of fatigue cracking, transfer cracking, its severity levels, and then again, what type of rutting that we have in our existing flexible pavement. The foundation support is what we've already discussed for rigid pavement overlays of rigid pavements in Module 8, and also under the inputs for Module 4-4 for concrete pavements or for concrete pavements for new rigid pavement design. So I want to go back now to, again, at the initial screen and very briefly show the short jointed plain concrete overlay of an existing flexible pavement. Again, it's very similar. The short jointed plain concrete where we have the asphalt, existing asphalt layer, and then the SJPCP as it's defined in the Pavement ME design software as the overlay of the flexible pavement itself. And again, all of the other is similar. I want to very briefly go to the performance criteria. Now this is for the short jointed plain concrete pavement. The only performance criteria that are included in the Pavement ME software for this concrete overlay, short jointed plain concrete pavements of the existing flexible pavements, is longitudinal cracks or percent crack slab with longitudinal cracks. The other performance criteria for rigid pavements like faulting as well as mid-slab cracking are not included. So it's only longitudinal cracks and percent crack slabs. That is the only one, basically the only one included. More importantly, there is, well, the reliability level can also be included. Now I'm going to go back to the general information, and I want to look now at JPCP over AC, or flexible pavements, in terms of the performance criteria. This is identical for new jointed plain concrete pavement design. The same would be true for CRCP, where we're placing a CRCP over a flexible pavement. The performance criteria is the same for a new CRCP pavement. These were previously discussed in Module 6-1 as well as in 6-2 for rigid pavement design. And we've already discussed the criteria for an asphalt overlay of an existing flexible pavement, where the difference is reflection cracks plus the new cracking of the new asphalt overlay. So all of those are basically the same. So with that, the other item that we would like to review has to do with the rehabilitation levels. So the rehabilitation levels are defined under the Design Properties folder under the tab called Rehabilitation. So I believe this will be AC over AC. So this is an asphalt overlay of an existing flexible pavement. Go back to the Design Properties for rehabilitation, and we can have input levels 1, 2, or 3. With input level 3, it's just a structural rating and environmental rating category. These vary from excellent to very poor for the structural, as well as excellent to very poor for the environmental rating. And then this is where the total rut depth basically gets entered, that's measured at the flexible pavement surface, or at the surface of the asphalt layer. Excuse me, the mill thickness, and for rehabilitation input level 3. Now if we go to input level 2, this is where the distresses from the visual distress surveys are entered. Bottom-up fatigue cracking, its severity, and then transverse cracking, the length of transverse cracking, and its severity. Bottom-up fatigue cracking is total percent lane area. For those, that amount of cracking that exists after the mill thickness. So the other important point here is bottom-up fatigue cracking does not include top-down cracking. So any top-down cracking should not be included in the area of bottom-up fatigue cracking. And then the transverse cracking is measured in feet length in terms of feet per mile, and then also its severity going from low, medium, high to user defined, just like for the severity level for fatigue cracking, low, medium, high, or user defined. User defined would be where the user measures it. It's very difficult and really impossible to measure the low transfer efficiency of fatigue cracks, especially its bottom-up cracks, because you do not know where all the bottom-up fatigue cracks are from the surface, because not all bottom-up fatigue cracks may have propagated to the surface. However, for transverse cracking, it's generally any transverse cracking that's there is basically assumed to have propagated through the asphalt layers. So the low transfer efficiency based on severity level, the default value used for low transfer efficiency is tied to severity level for low, which is 0.8, medium, which is 0.4, and then high, which is 0.1, or it can be user defined, whatever that user defined, because this can be measured for flexible pavement as well as rigid pavements, which was discussed in Module 7, or General Pavement Rehabilitation items that pertain to the Pavement ME design software. We're also going to mention it again within this module, as we did under Module 8 for rigid pavement rehabilitation. So that is basically input level 2, or rehab input level 2. Rehab input level 1 is different in that for this screen, under the distresses, there is no fatigue cracking that's entered for the amount of bottom-up fatigue cracking. There is for transverse cracking, there is for the rutting. That is all as what we've previously discussed for input level 2. The difference is the fatigue cracking damage, bottom-up fatigue cracking damage, is not defined by the amount or area of bottom-up fatigue cracks, but is defined by the amount, by the back-calculated elastic layer moduli. So if we go to our structure, go to the existing asphalt layer that's present, the mechanical properties, you can see now that these are the inputs for the modulus of our existing asphalt layer that are obtained from non-destructive deflection testing. Non-destructive deflection testing is not discussed within this module, but Pavement ME has an associated software program called the back calculation tool, where the different layers, or the elastic modulus, resilient modulus, are back calculated from the deflection basins through the BCT tool, the back calculation tool. And those values, at least for the asphalt layer, are entered here. So I'm just going to, as a demonstrate, just go down to where we only have one layer. The back calculated layer modulus for the existing asphalt layer, for the existing asphalt layer, would be entered there. The frequency of the falling weight deflectometer, which is 30 hertz, would be entered there. And then whatever the mid-depth of the pavement temperature entered, let's say 75 degrees, would be entered here. And with that, that's input level 1 for the asphalt layers. And for rehab, input level 1 for determining the modulus of the asphalt layer. For the other layers, like for let's say our unbound layers, like our subgrade, the modulus is entered also for the back calculation value, whatever our back calculated value is, directly from the FWD, or the back calculation tool. And let's say if this was 24,000, and we apply our C factor that we will discuss later in the message, then that's the inputs for rehab input level 1 for the unbound layers. So the back calculated resilient modulus is entered, and then the C factor, which we'll define later, for this specific design strategy and type of layer, is entered in this window here. And basically the resilient modulus that's used by the Pavement ME program is simply the back-calculated resilient modulus multiplied by the C factor, 24,000 times about 0.35. And that is the resilient modulus that's used as a starting point for the Pavement MED program for flexible pavement rehabilitation. The other item I want to make has to do with the information under the volumetric or the sieve tab, and that is if we're entering the back calculated layer modulus within a flexible pavement rehabilitation, we should enter whatever the dry density or dry unit weight of the subgrade that was measured at the time of FWD testing, as well as the water content that was measured at the time of FWD or falling weight deflectometer testing to be compatible with our resilient modulus that's back calculated at those volumetric conditions. If we do not have the volumetric properties, if they're unknown, and we're going to use the default values for each of our unbound layers, then the resilient modulus to be used basically should be the default resilient modulus for the specific layer and not use the back calculated layer modulus values. But back calculated layer modulus values provides very good information for any rehabilitation design, so the user is encouraged to enter the back calculated layer modulus, the C factor, and then also enter the measured values for the dry unit weight and water content of each of the unbound layers, which would be any base material, subbase, as well as subgrade strata that were used in the back calculation tool itself. And or estimate what these values may have been at the time of FWD testing using external processes. Pavement MED does not have that capability to backcast what the moisture content and dry unit weight were, but there are tools that the user could use to determine what the equilibrium dry unit weight and water content were for different climates as well as different types of materials. So with that, we're going to go back to, I think we've now covered most of the information we wanted to include. So now we will go back to the presentation. That concluded part B. This next part of the presentation is going to be referred to as part C within Module 9. So Module 9 basically has three parts. Part A was the condition assessment and the initial part of evaluating the flexible pavement for rehabilitation design. Part B was going through the software, and now part C is going to be going through the different overlays and defining the distresses as part of a flexible pavement rehabilitation design. So this basically concludes Part B.